Now we operate with the assumption that that clock is correct. Is it? It is, all right. Plus minus 50 seconds maybe. There it is. So welcome back to computational statistics. We're going to cover some of the very basics, potentially not very useful ideas that separate Bayesian statistics from other types of statistics that maybe you have come across in your, especially undergraduate education. So these ideas are very good to know, but after a little while, they will not mean anything because somehow they're all common sense, okay? But we need to review them, and I do provide in the slide some notes on other type of statistics you may have seen before, but intentionally I'm not going to discuss them during the lecture, okay? So you can read them because they are important to understand why we do what we do, but I don't see a point of us discussing it, considering we don't have much time. So if time allows, and I hope it does allow, I want to discuss in some detail the exponential family of distributions. And we need to discuss it not only because it's important, but also because your homework contains something about the exponential family of distributions. So I will do maybe the homework today, sort of. Okay, but I want to do some more advanced calculations if time allows. All right, this is the Reverend Thomas Bayes that wrote a single paper that has revolutionized basically information sciences. So when I was in visiting the University of Edinburgh in May, they're building some new institutes on data sciences, and everywhere they had his picture with a label, our former graduate. And it's like, give me a proof that this guy was a graduate of the University of Edinburgh. But obviously a university with a long history, right, can claim that. So they claim that he passed from Edinburgh. I suppose everybody does, one time or another, right? I did too. All right. So we're going to be doing a lot of jumping. This is my jumping sort of indicator here. So we're going to go to slide 9. And so let me start with the bottom, something you already have seen. There's nothing strange about this. So let's consider maximum likelihood estimation of the mean and the variance for the Gaussian. By the way, I realize the pointer never comes across on the videos, so I need to point at least or say something which equation I'm referring. So let's say that we have n samples from a Gaussian, univariate Gaussian, and we want to compute the mean and the variance using maximum likelihood estimation. So when you do all the calculations the way that you see on the bottom equation, this is the likelihood for a single sample. You take all of this to be independent for all the samples. You do the calculation, you put the product inside an exponential, you get a summation, and effectively you get what you see on the bottom. Common sense derivation, there's really nothing to it. But what I want to remind you in this calculation, first a notation theta, theta 1 is mu and theta 2 is sigma squared, just to simplify the notation here. But you notice in the likelihood, you do get all the data coming in two simple scalars. One is the sum of the xj's, and another one is the sum of the xj squares. So we call this two terms the sufficient statistics for the estimation of theta. Can you see why the name sufficient statistics? What does that mean? So, maximum likelihood estimation, right? We're going to compute theta by maximizing this, and we say we will call this the sufficient statistics. So what does it mean? Common sense language here. Remember, time is gold. I have time that every slide will be 30 seconds, so your answer has to come in 10 seconds. So what does it mean that these are sufficient statistics before we formally discuss it? I mean, how do you understand it? Because if it makes sense as a common sense definition, then we're okay. Why we call this sufficient statistics? There is no distribution here. We want to determine theta, so why for the determination of theta through maximum likelihood we call these two summations the sufficient statistics? Because the only way that the data come to affect the evaluation of theta in this function is through these sums. You see that? It's not like every term comes individually in some strange way. Is at the end of the day, if you have n data points, this summation is what defines theta. So basically, as the data comes, I can get rid of it and say, look, I only keep track of these two summations because alone they can define the maximum likelihood estimate. We agree? All right. Now, I am going to try to generalize the concept of sufficient statistic, right? But I am not going to do a good job here because it requires some knowledge that maybe we mentioned a few things on conditional independence in one of the earlier lectures. But let's consider that we have some parameters theta that we want to compute. This is what I just defined as sufficient statistics of the data x, and this is the data x. So the way that we introduced it with a common sense language was that T of x is everything I need to know to compute theta. All right? So, so if somebody gives you another information about x, it is not relevant for the calculation of theta. But in the way that I have it here vectorially, it basically, this picture, and we will have more of this in another course, it basically says that if I give you the sufficient statistics, so if I give you those summations, x and theta are conditionally independent. Right? So basically x doesn't depend on theta given T of x. So if you know T of x, you don't need to know anything about x to relate that to theta. T of x contains all the information about theta. Now somewhere in an earlier lecture, I gave you a decomposition which I also proved it using this independence relation, and it says basically that my likelihood here, you can accept this as is, all right, so that I don't have to elaborate a lot, is basically some function of T of x and theta times some function of x and T of x. And in this particular case, these are conditional probabilities since I use this directed graph. Okay, so again, with the definition of the sufficient statistics and the independent statement that I mentioned, that given T of x, x and theta are conditionally independent, you can factorize the likelihood, the probability of x given theta, as, in this case, a function of T of x and theta, and a function of x and T of x. Okay? This is very important. Okay? It tells you that theta comes in one function together with T of x, not with x. Maybe you don't remember, but somewhere in the slides on conditional independence, I did mention that conditional independence leads to some factorization that looks like this. So you may want to go back and look at this at an earlier slide. Okay. So in our Gaussian, these are the two terms. It is important to note that they're scalars. So the data can be an infinite number of data, n can be huge, still the sufficient statistics are scalars. This is very important. So, are they unique? Of course not. For example, I can scale this thing, divide by n, or I can use this. My data variance. These are also sufficient statistics, and I can write things in terms of the sample mean and S square. So, but more or less, these two variables define my sufficient statistics for the estimation of mu and sigma squared. Okay, we jump to slide 12. And let me just put a few things up. So, I would like you to guess now what the sufficient statistics would be for this example. Suppose my samples come from a uniform distribution from 0 to theta, and theta is my unknown parameter that I want to come up with a maximum likelihood estimate. Okay? So again, I have a sample from a uniform distribution from 0 to theta. So this is actually my likelihood, the way it looks like. This is the indicator function, right? So if xi is from 0 to theta, by the way, uniform distribution means 1 over theta, but obviously xi needs to be on the interval 0 to theta. Okay, so this is an indicator function that multiplies 1 over theta. And if I have n data set, n points, I can write this as such. Do you agree with this? So if I take all of this and multiply them together, can I write them like that? From where is that coming? Remember, this will be, all of these terms will be, that come in this product basically, will be non-zero if xi is from 0 to theta. So theta has to be from where to where? From a maximum of xi to infinity. So what's the sufficient statistic for the calculation of theta if I do maximum likelihood estimation here? Maximum of xi. Nice. All right. So things can be weird looking. Okay. Now I'm going to jump to slide 14. There are many more examples in the notes that you should consult so you can get a good idea of the sufficient statistics. So let me state the sufficiency principle. Okay, so let me read it. If you have two observations, x and y, that have the same values of sufficient statistics, okay, then the inferences about the parameter theta based on x and y need to be the same. I repeat, if you do two experiments, right, you collect data x and data y, and they have the same sufficient statistics, then when you do inference about the parameter theta of the distribution, all right, then the two inferences have to give you the same value of theta. So if you do, let's say, maximum likelihood estimation, you should get the same if you use x, the same if you use y. And again, that's a common sense because we said that what defines the estimate of theta is the sufficient statistics. Obviously, if they're the same, then the same estimate will come out from this for theta. And here is a proof, for a simple case. Let's say we have samples from a Gaussian, and to make things simple, we take the variance to be known, equal to 1. So the only sufficient statistic is the sum of the xj's. So if somebody tells you, you collect some data xj and some data xj prime, and the summation, this summation is equal to the summation of xj prime, then the MLE estimate needs to be the same, which is no problem because remember the MLE estimate for the Gaussian is the sample mean. So you have this divided by n, and obviously this divided by n is the same as xj prime divided by n, summation, all right? So the two estimates are the same. Now, you may say this is, obvious, yeah, but, I'm not going to go through. On the bottom of the slide, I have another estimate because, you can come up with your own estimator for the parameter theta, in this case, the parameter mu, right, that violates the sufficiency principle, okay? So don't take that every estimator that you come up with satisfies this, but you need to be sure that it does. Okay, so we're at slide 14. I'm going to jump to slide 17. Another principle that we need to be sure that is satisfied, and again, it's a common sense principle. In the inference about the parameter theta, the information brought by an observation is entirely contained in the likelihood function f of x given theta. I mean, obviously, we work up to now, we haven't really done anything else with the MLE estimate, right, by maximizing the likelihood, but the likelihood principle tells you the information that comes from any data point is contained entirely in the likelihood function. And obviously this implies that if I have two likelihood functions that they are the same, I better get the same estimate, or that they are proportional to each other. I mean, if they're the same, it's not an issue. If they're proportional to each other, then my estimate for the parameters theta needs to be the same. So if you have a likelihood that looks like some function of x times another likelihood function, the estimation, when you do maximum likelihood, for example, the estimate that you get for theta from here and from there has to be the same. Is it? So if I maximize this function with respect to theta, do I get the same thing as maximizing this with respect to theta? Yeah, because C of x does not depend on theta, okay? And I refer now to maximum likelihood estimation, right? But obviously, we're going to do lots of different type of estimations in this course, and we only have seen maximum likelihood, and that's why I refer to it. But basically, any sort of estimate that you come up for these parameters needs to satisfy this likelihood principle. Okay. Now, remember I told you that I would not emphasize the standard statistics that you maybe learned in other courses, or maybe you are still learning, taking course in HCMS and elsewhere, all right? Most of the non-Bayesian statistics does not satisfy the likelihood principle, okay? And I'm not going to elaborate on it, but for example, for those who know ideas of, and I put those things last night on p-values in the slides, in a lot of calculations that you do in non-Bayesian statistics, you integrate over the data space beyond the observed data, basically. You do calculations that don't necessarily involve the observed data, and all of those calculations do not obey the likelihood principle. And I have a very nice example of two distributions in the notes that have proportional likelihoods, but when you do compute the integrals like this, they will basically give you different sort of, and this will not be estimation of parameters, but maybe different decisions that you will make out of this analysis. Okay. I'm going to give you one example that is the most famous example in the literature on why you really need to be Bayesian, okay? It's one of these simple examples. By the way, if anybody has time, the website of Professor Vidakovic from Georgia Tech has a lot of nice sort of lecture notes if you want to visit on this type of calculations. So let me do a simple example to demonstrate how you can be in trouble with this likelihood principle. Let's say that we take samples from a binomial distribution. So, you know, you fix the number of coin flips, right? And you want to decide if the coin is fair or not, okay? So theta is the probability of being heads. And so fair means theta equal to 1/2. This is the alternative hypothesis, theta greater than 1/2. So we predetermine, this is important, that our experiment will be that we will do 12 flips of the coin. So we do 12 and we collect data x equal to 9 heads. So the likelihood looks like that. Everybody agrees? Okay? All right, so out of 12, 9 is heads, so theta to the 9th, 1 minus theta, 12 minus 9. It looks like that. All right, in non-Bayesian statistics, to decide if the coin is basically fair or not, you calculate the probability of observing data, in this case x equal to 9, but also extreme data, so for x greater or equal to 9. Okay? So in essence, you're going to have to sum this for x equal to 9 and x equal to 10 and 11 and 12. Okay? So this is what is called the p-value that people in non-Bayesian statistics compute. And in this case, the p-value comes to be below this critical level, and you say, oh, you know, the coin is fair. Okay? Again, I'm not going to bother you if you don't know anything about p-values, but I am only going to say this is one test you do, and the likelihood looks like theta to the 9th power, 1 minus theta to the 3rd power. So let's do another test. The same coin problem, but now I am going to flip the coin until I get I get 3 tails, basically. So when I get 3 tails, I stop and I say that's the end of the experiment. Before the end of the experiment was basically I'm flipping it 12 and I'm measuring how many heads I get. So now the end of the experiment is when I get 3 tails, all right? So when I get 3 tails, the data I collect is that I have 9 heads. Okay? Do you know what distribution is that? When you do coin flipping until you get certain number of failures? Negative binomial. So if you search more, and it's in the slides, the details, effectively the likelihood looks identical minus some constant term. But if you calculate this p-value, which is the non-Bayesian way of making decisions if the coin is fair or not, basically your decision is completely different from the previous test, and as a matter of fact you say that the coin is not fair. So basically a non-Bayesian statistician, even though the likelihood is identical, will make a completely different decision from a Bayesian statistician. To be honest, and I have talked, of course, you know, I know lots of statisticians in my life, even those who are fanatic against Bayesian statistics, they are all working in Bayesian statistics now, okay? So it doesn't mean that there are no other ways of doing things, but effectively anybody who doesn't like Bayesian is left behind, way behind. All right, we're at slide 21. Let's see, we're going to have to jump to slide 24. 24. I'm only going to mention the bottom because, you know, we don't really have the luxury to philosophize. So you notice in the previous example that I demonstrated with the coin flipping, we decided when to stop the experiment. In one case, if we flip the coin 12 times, in the other, if we get, you know, 3 tails. So the stopping rule principle says inference about the parameter theta must depend on the stopping rule only through the sample. So you cannot just say, I'm going to stop the experiment when the sun goes down or when this happens, etc. Only you can, if this is a function of your data and you stop based on the data, that's fine. Otherwise, you get in trouble. Okay? So this looks like, again, a common sense decision, but the idea here is in Bayesian statistics, the data decide about your inference, not other rules that you introduce in the process. And I think I have another example, if I can find it, that is a very historical example. This is a nice example. Okay. So let's do the following scenario. We have a probability that x can take the value theta minus 1 or the value theta plus 1, and we assign the same value on these 2 probabilities. Okay, so this is our model, and we want to make an estimate for theta, and so my rule that I have here for estimating theta, this is my estimator. It's not a maximal likelihood estimator. I just postulate, you know, a common sense estimator. It says if I take 2 samples and they're not the same, then I'm going to take as my estimator of theta to be x1 plus x2 over 2. Do you agree with that? Does it look a good estimator? If the 2 samples are not the same, all right, so if one is theta minus 1, the other one is theta plus 1, don't you see that the average basically will give me theta? Nice. And it says now, if the 2 samples come to be the same, I'm going to take as my estimator of theta to be x1 minus 1. Now you notice that if it happens that your sample is theta plus 1, this works. But if your sample is theta minus 1, this gives you the wrong answer. So according to what you see now, without any data collected, how often you are right with this estimator. So you remember, you can have the following scenarios. The two samples can be different. So there are two cases like that, right? I mean, the first can be theta minus 1, theta plus 1, or theta plus 1, etc. Then both samples can be theta minus 1, and both samples can be theta plus 1. So what is the probability of going wrong with this model? 1/4. Okay, so 75% of the time you will do well with this model. Okay, now here's the idea. If you now are starting collecting data and you try to make some inference on the parameters theta, should you use the fact that this model is wrong 25% of the time? Should you bring on the table the fact that the knowledge, this is wrong 25% of the time? The answer is, if you're a Bayesian person, no. All right? The answer is, your inference has to depend on the data, nothing else. So once you say, this is what I do, this is my experiment, the data have to decide, your inference about theta. And this is what is called the conditionality principle. There's actually one of my friends from another university, not to mention, he loves to find paradigms on the other direction, where basically Bayesian inference gives you very wrong results, but actually they are sort of, if you don't have any data, if you don't have this, and if the universe blows up, then that's what happens, okay? But there are paradigms on the other direction as well. Okay, slide 27. We proceed, let's see. So we just take this, so we don't need it. So summary. At least in the context of maximum likelihood estimators that we have seen, they satisfy basically the likelihood and the sufficiency principles that we discussed. Okay, so once you select an experiment, okay, all of those are satisfied, and basically the proof is on these two equations that you see there. We're jumping way down on slide 39, okay? And this actually would be a very easy slide, so you have to go very fast. So basically, the ingredients of a Bayesian analysis, either in estimating a parameter or evaluating a hypothesis, in this case age, will it rain today or not, all right? So they involve a prior model for your parameters of your hypothesis. They involve the likelihood that we discussed extensively on the last lecture. And of course, from those two, through the Bayes rule, you get the posterior. So the posterior is a distribution. It's not like a point estimate, like maximum likelihood estimate. It's a full distribution, and a full distribution is much richer information than just a point estimate. Okay? So again, you may ask me actually why I use all these different symbols, pi, f, and etc. And depends what book I was reading when I was writing these slides. Okay, the idea is, yes, we treat this as a function, so it's a good idea for the likelihood not to put a symbol for probability, and the same thing with the marginalization factor on the bottom that I'm going to come later on. But the prior, if you use a pi or a p, it's the same thing, okay? If you use something different in notation, it's also good, but you need to know what you're doing. Actually, I don't need slide 40. You know what I need? I need slide 43. So you may ask, is a full Bayesian analysis basically when we compute and use the posterior distribution for making decisions and inference, do they satisfy the sufficiency principle, and do they satisfy the likelihood principle? And let's pick up one of those. For example, let's take two likelihoods, but they differ by this function of x, c of x, and you compute the posterior. You notice C of x cancels in the numerator and denominator, because the denominator involves the likelihood. It's the marginalization is, the integral basically of the term in the numerator. So C of x and C of x cancel out. So basically inference through a likelihood F1 or a likelihood F2 gives you the same answers basically for your posterior distribution. And the same thing with the sufficiency principle. Something very important that I'm going to try to emphasize in the follow-up slides as well. Notice that any integrals that appear in Bayesian statistics are integrals in the parameter space theta. They are not in data space. Okay, non-Bayesian statisticians integrate on data space that includes data that they have never observed. Here, all integrals are in the parameter space. This is very important. All right? I mean, this term is the marginalization of this distribution, right? So obviously, I'm going to integrate in the parameter space. This is my posterior, and this is the anormalized version of the posterior on the numerator, so that the integral makes this a normalized posterior distribution. So if you have the posterior, not that you'll be interested just in point estimates, but you may ask, we had a maximum likelihood estimate, so let's formally see all the point estimates that somebody can get with the posterior, okay? So the first one is the map estimate, which the maximum posteriori estimate is maximizing basically the posterior with respect to theta. This is similar to maximum likelihood, but it differs from maximum likelihood because now there is a log of the prior there. So you know what mathematically does this, why this is a better estimate than the maximum likelihood? This goes back to this concept of regularization, right? If something is not well posed, all right? So maybe maximizing the likelihood is not a well posed problem. Adding this term here stabilizes the optimization problem to give you a nice stable estimate, which is the map estimate, okay? So in mathematics, with no affiliation to statistics, lots of people will go when they do optimization and add the regularization term. The regularization term in the maximum posterior estimate is the log of the prior. So the prior stabilizes the process, okay? And gives you a good estimate, even if you have very limited data, for example. If you have very limited data, still this will work. Now, the map estimate is, lots of people use this, and actually some machine learning books, they prefer to only work with the map estimate, no statistics or anything else, because it's good for what they do. Often it's the wrong measure of the posterior, okay, and we will do examples actually throughout the semester. Another point estimate may be the posterior mean, and this is the calculation of the posterior mean. Right, so you have your posterior, this is the posterior mean. Obviously, you have to integrate in the theta space, and that can be problematic because if this distribution is known through a code, this will require very high dimensional integration, and it won't be an easy thing to get. And of course, you can get a posterior quantile. So, for example, you can ask yourself, what's the probability that theta is greater than some value, than 0.5, let's say? And the only thing you have to do is integrate from 0.5, let's say, to infinity, the posterior, okay? So when it comes to point estimates, this is what you need to remember. Map, posterior mean, posterior quantiles. And of course, when we start talking about Monte Carlo methods, we will abandon all of this and work directly in an implicit way through the posterior distribution and figure out how to get samples from there. So let me jump. Slide 49. And we'll do an example, trivial. Okay? So coin flipping again, just playing with the posterior. So let's say you want to check basically the hypothesis that the coin is fair, similar to what we had before. Versus the alternative, let's say, hypothesis, H2. So obviously, this is prior probability sum to 1, but we do know what pH of 1 is and pH of 2. So let's say you do an experiment, you flip the coin 5 times, and you measure 5 tails, okay? Would you agree with me that if this is a fair coin, that the likelihood is 1 over 2 to the 5th, right? I mean, it's a fair coin, probability 1/2 to get heads, so and tails, so the likelihood is 1 to 2 to the 5th. Now, with the hypothesis that always, let's say, H2 is that always you get tails, what is the likelihood of this? It is 1, all right? So if you want to compare two hypotheses in a Bayesian way, and you form this ratio, by the way, we're going to do this formally, maybe in 1 or 2 lectures using this concept of Bayes factors, but if you want to start with and you want to compare this hypothesis, you will form the ratio of the two posteriors, and then you will decide which way to go based on which one gives you the highest values, okay? So both of these distributions have the same normalizing factor, which is cancelled, so you don't see it here. So what you see is the likelihood with hypothesis H1 times the prior of H1 divided by the likelihood of H2 times the prior of H2. So you plug in this 1 over 32, and now you see, to make a decision with this data set as which way to go, if the coin is fair or it always gives you tails, unfortunately it depends to a significant degree on what priors you use. All right, so this will not be sort of a very good exercise in inference in a Bayesian setting, because if you already believe that this is a fair or not coin, this will dominate your decision process. Okay? In other ways, this was not a very informative data set, but you may get in life those, and they can throw you out in your decision process. If we do a full Bayesian analysis for a single example, let's say the probability that the coin is will draw heads is from 0 to 1, and we don't really have a lot of information, so we take this prior to be uniform, right? So it can be anywhere from 0 to 1, okay? So it can go all the way tails or all the way heads or somewhere in between. So this is our prior. This is the data we collect, and then I claim that the likelihood looks like that. You agree? 2 heads, theta squared, 1 minus theta cube. It's a binomial distribution. And the posterior basically looks like the likelihood times the prior divided by the normalizing factor. And the prior is a uniform distribution. And I would like you to get very familiar with this beta and gamma and all of these distributions, because immediately, if you have theta squared, 1 minus theta cube, this is a beta distribution, beta with parameters 3 and 4. The beta distribution, I remind you, is x to the alpha minus 1, 1 minus x to the beta minus 1. So this will be 2 will be 3 minus 1, and this will be 4 minus 1. So this is, the posterior is a distribution, beta of 3 and 4. And depending on the data sets, basically you can get very weird distributions, right? And they have here 3 different data sets, different from this one, and it shows you how the posterior looks like. Okay, it's basically the same example. Now the only difference from the previous example is my prior for theta is not a uniform, but is a beta distribution, okay? And again, you have to recognize that the posterior comes out to be a beta distribution in a closed form. By the way, since I'm going to talk about the exponential family today, notice something interesting. In this problem, if your prior is a beta distribution and the posterior comes as a beta distribution, that's fantastic. And in that case, we call this prior to be what to the likelihood. So when you have a prior that is such that when you multiply with the likelihood, it gives you a distribution of the same family with different parameters, we call the two things what? What's the nice word? Conjugate. Okay? So many things in statistics, okay, they use basically conjugate prior models simply because the only thing you have to do when you collect data is update the parameters alpha and beta. Okay? And this is sort of a trivial example on doing that. All right, so we don't need this. Okay. I think I have used this concept of prediction before, but I have not really said much. You know, in Bayesian statistics, right, okay, the posterior is nice, but that's not all the reason why we do Bayesian statistics. You know what? You flip the coin 10 times and you get some data and you compute the posterior, but really what you're interested is if I flip it once more, will it be heads or tails? You want to be able to make predictions, right? We want to know if it rain in August, in the first week of September, will it rain tomorrow, right? This is what is all about in Bayesian calculations. So what we need to do is we need to compute the so-called predictive distribution or predictive posterior distribution. And let's set it formally. This is a very important calculation, by the way. So let's say that you collected data X. So X is not one data point, it can be a whole collection of data points as we have done up to now. So you computed your posterior, and now you want to compute the probability of observing data X hat. So in the coin example is, if after I collected X and I do one more coin drop, will I get heads or tails? So X hat refers to prediction. X is the data that you already have. And the calculation for computing the probability of X hat given X is called this predictive posterior distribution. It comes up in a very simple manner as follows. So let's do the algebra carefully, okay, because you will have to do lots of things like that. Do you agree with me? I can write this distribution. Think of this and everything else being a probability function. Can I write this as such? What rule of probability is this? The what? Sum. All right, I'm summing in theta. Remember the sum rule of probability. Okay? So I am writing this now. Okay, I'm going from here. I am writing this as the joint probability of X hat, theta, and X divided by the probability of X. Can I do that? What rule is that, by the way? How can I go from that probability to this? The conditional, which also fits under the product rule in some sense, right? I mean, that's the only two rules we know, so we write it like that. So let me divide and multiply by the probability of theta and X, okay? This is probability of theta and X. And if you look at the first term, what is this divided by that? It is the probability of X hat given theta and X. You agree? The first term, you agree? And what is this? Is the probability of theta given X. And now I simplify to go to the last term, and I drop X there. Why is that? This is very important, right? I say, well, X, if I know what theta is, I don't need X. Right? Because you remember the likelihood model is given theta compute X. So if I know theta, I don't need X. Okay? So here is the predictive distribution. Very easy to remember. What is the probability of X hat given theta? It is the likelihood of, what's the likelihood of X hat? So this is the likelihood of X hat. And what is P of theta given X? Is the posterior of theta after I observe data X. You remember our experiment? We do collect data X, we compute this posterior, and now once you have that, if you want to compute a predictive distribution of X hat given X, it's basically the integral in the parameter space of the likelihood times the posterior of theta. And by the way, compare this with the normalizing factor in Bayes' rule. So this is the predictive distribution, and this is the marginal of X hat. The difference is that the probability here is the prior, the probability for predictions is the posterior. Okay? All right. So we have seen the predictions, and this again is called the predictive posterior or simply the predictive distribution. So here is a simple example. The coin flipping thing. So theta is the probability that we draw heads. We have some prior which is uniform, and we collect this data. And in the previous slide, I think this is the example we did. It comes up that the posterior is a beta distribution with parameters 3 and 4. So if you want to do predictions, so you're asking, right? If I throw this coin once more, will I get heads? So considering that I have observed this data, what's the probability that my next row will be heads? So again, our formula will be the likelihood of X hat. And you remember for this problem, the likelihood is theta, that's the probability of getting heads, times the posterior, which was our beta 3 and 4, it's there. And immediately you can see we have a theta cube here, 1 minus theta cube. You know, on the top you can recognize the marginalization of a beta distribution divided by this beta factor, and you can get an answer, and the answer is 3/7. So if you really want to play smart with your friends, you can use this type of calculations to cheat without telling them you know much about statistics. Okay, 56. All right, we better run because there is a lot of things we need to do, and I am not going to bother about this. Okay, so let me stay on this slide, and I will explain it only with words. Bayesian analysis is sequential, right? So I think I had mentioned in an earlier lecture, if you collect data, right, every time you collect data, you can go and update your posterior, right? Which means, up to now we said this is the likelihood multiplied with the prior, and there's your posterior. But if I collect 10 data points, maybe I want to compute the posterior with the first data point alone, and then I can compute the posterior when the second data point comes, but I need to be careful. In that case, my prior has to become now the posterior after I collected one data point. And the proof is basically on this slide, okay? And the key ingredient in doing the proof is the following, that in the likelihood calculation, if you look at the likelihood of data X and data X star, because the data are basically condition independent given theta, you can factorize this function as what you see there. In other words, it doesn't matter for inference purposes which data point comes first, which one comes last. At the end of the day, when you finish, you will get the same inference or decision when it comes to the parameters theta. Okay? So the idea is, if you already have collected data X, right, and you're asking what is the posterior of theta given both X and X star, what I can do is I can use the likelihood of X star only, but instead of carrying the prior here, I'm going to plug in the posterior given my data X. All right? So the idea is, just remember, inference in a Bayesian setting is sequential. It doesn't matter how you collect the data. You just need to be sure that as you proceed from one data point to another, you update your prior to become a posterior using the data you collected up to that time. Okay? And the only thing you need in the calculation is this factorization, basically, is condition independence of the data x and x star, and the rest is just, it's a trivial algebra. This, by the way, it's wonderful, because if it is not the case like that, right, when you have big data, if you wait to collect all the data and then make inference, you're going to be in trouble. But this allows you to constantly be able to do predictions, even one data point at a time, okay, with the idea that this posterior will actually converge, and you can even say to yourself, I don't need more data, now I am good enough, you know, thank you very much, okay? So this is a very nice feature of Bayesian analysis. One slide before I move to a more interesting topic. Yeah, so you remember we defined the posterior, we talked about point estimates of the posterior, we defined the predictive distribution, very important. We said nothing about the marginalization on the bottom of Bayes' rule. And you remember that involves the likelihood times the prior and integral in the parameter space. Okay? Now, if your objective is to calculate the posterior, okay, 95% of the times you don't really need to know this. So if, for example, if you're going to draw samples from the posterior, you don't need to actually normalize the posterior distribution. You don't really need this. If, however, your objective is to compare different models, okay, so to do, let's say, what's called model selection, then model selection will be based entirely on this marginal distribution of x. At the end of the day, right, you collect data x, and you want to basically figure out what is the model that gives you the highest probability, this marginal distribution of x. Because if you have two models to compare, who cares what parameters one model uses and who cares what parameters another model uses? The only thing you care is the probability of the data under this model higher than the probability of the data under another model. Okay, so if you want to compare models, that is based on this marginal distribution of x, and we will spend one lecture on this. All right, so we're going to come back because it's extremely important in a Bayesian setting. Okay, so we can now take a break. It's 4:22, and let's see what slide is supposed to go. We're going to start a new topic, which actually will tell you that Bayesian analysis can get complicated, but also, you know, can be generalized in a way that one model will allow you to do predictions for thousands of other similar models. And to do that, we have to discuss what is called the exponential family of distributions. This is your homework set. I'm assuming you already have worked problem, what was it, 1 or 2? So you don't, all of this look very familiar to you. So let's define it. When it says family, right, it implies many, many distributions that fit under the same model. So if we manage to do inference in this general form, we have included many, many distributions. And the results basically transfer from a Gaussian to a beta to a gamma distribution, etc., to any distribution that fits in this category of what is called the exponential family of distributions. So what's the exponential family of distributions? Is the distributions that fit in this form that you see there, where these parameters theta are what they call the natural parameters of the distribution. By the way, you maybe forgot, but last Friday we were talking about an alternative way of writing Gaussian processes. You remember? I mean Gaussian distributions. The canonical form of Gaussian distributions. That actually, when you look at it, fits directly on this exponential family. Okay? So let's see what we have. We have some parameter theta, and a factorization that has an exponential, that's why it's an exponential family, of eta transpose, so obviously eta is a vector, times u of x, all right? This exponential will be what tells you if potentially you have an exponential distribution, times some function of theta times some function of x. And you can rewrite this in a slightly different form by plugging in this g inside the exponential. And how do you do this? By defining this function of theta as minus log of g. All right, so you can put this inside minus log of g. Now, you can also write this, with the normalization factor explicitly given, as you see on the equation at the bottom, right? So you can have a normalization factor explicitly, and this normalization factor is basically 1 over g. I mean, you can see immediately if you integrate this distribution in x, right, you should get 1. So 1 over g is the normalization factor of this distribution. Okay? So, now, why are we studying the exponential family? We study because by spending some time talking about this, we're basically accounting for doing Bayesian inference for many, many, many different distributions. And whatever results you come up with for this distribution, you basically can transfer them to many other distributions that belong to this exponential family. So we want to study what are the properties of these exponential family distributions, and things will get a little bit tricky now. And I have to admit, even the lecture on Wednesday, I'm going to post the slides so you look at them, because we will come up with some results that may look a little bit complicated, but they're not. So let's do an example. And this is your homework, by the way, so I appreciate that you thank me. This is the Bernoulli distribution. So heads means x equal to 1, x equal to 0 is tails, and the probability of heads is mu. So what you see here on the top equation is the moment parametrization, right? Mu is the mean of the distribution. That's the moment parametrization. So we're asking, is this an exponential family distribution? Well, if you get trained to do these tricks, can I do this? Can I write this, the exponential of x log mu and 1 minus x log of 1 minus mu? Yeah? I mean, this is log of mu to the power x, this is log of 1 minus mu to 1 minus x, all right? And I have exponential, and if I get rid of the exponential of the logs, I get back to this, all right? So, yes, I can, and to put it on this form, right, this is our general class of distributions, I can keep my x log of mu divided by log of 1 minus mu, and then the log of 1 minus mu and x I can put outside as 1 minus mu. So there's my g of theta, all right? H of x equal to 1 here, and these are my parameters eta, which is this log of mu divided by 1 minus mu. Okay? So the Bernoulli distribution belongs to the exponential family of distributions. Now, I want, so I write basically all the generic symbols that we had here. I write them on the bottom to tell you explicitly what every term on H and G and U are. Okay? So I forgot to mention, and if I have time, I will justify it today. This U of x, you know what it is? What name should I give to U of x? We use it today in the beginning of the lecture. Look at the distribution, right? And there is eta transpose U of x. So what do you think U of x will come to be by miracle? The sufficient statistics for this distribution will be some function of the data that defines basically the parameter theta in that distribution. Okay? That's another major thing. Okay? But let me tell you another extremely major thing. Okay? So what we study up to now with this moment parameterization, it was written in terms of the moments like mean and variance, notice from here when you do this, the coefficient eta, these natural parameters, is the log of mu divided by 1 minus mu. So when you invert them, you can, first you notice that you can compute the moment as a function of theta. And this is a unique property of the exponential family. You can go from moments to eta in each direction you like, okay? And it comes out nice that the mean mu, it is basically a sigmoid function of eta. Now, you may say sigmoid function, what is that? Well, if for those who have taken any other course in machine learning, immediately you say, wow, that's interesting, okay? So it comes, for now, what we're interested is we can reverse this and write mu as a unique function of eta, which in this case comes to be the logistic sigmoid function. Can you do this with other distributions? Let's see. Can you do this with a multinomial distribution? So it's like the Bernoulli, but now we have mu states, and each of them can happen with probability mu k. So yes, you can actually from there, you can write exponential of the sum, and there is the parameter theta, and it comes out that eta k is log of mu k. But there is a problem here. When you write this distribution, that function a is not there, 0, okay? And later on, we will see that if that function is 0, we have a problem because this will predict that the moments will be 0 of the distribution. So just accept the fact that this alpha is 0 is not good news. Well, and in reality, this is not 0 because this derivation is wrong. And can you tell me what exactly? Well, it says there on the bottom. All right? What is wrong is that these parameters mu, from mu1 to mu_m, they're not independent. They have to satisfy this, the sum has to be equal to 1. So what you need to do is, in this expansion, you have to get rid of the last term, mu subscript capital M, and you write this in terms of summation from k1 to m minus 1. And when you do that, with some trivial algebra, it comes up that nk from 1 to mu minus 1 is given by ln of mu k over mu capital M, where you have defined this mu of capital M to be 1 minus the summation from k to m minus 1 of the of mu k. So multinomial distribution, of course, then it's an exponential family distribution, and you can compute the moments in terms of the natural parameter theta, and there is the calculation with some simple algebra that you see on the slide that I advise you to look, and it comes out a beautiful function, exponential of eta k divided by 1 plus the summation of these exponentials. And what function is that? My friends from computer science, do they recognize this function? What is that? Softmax, okay? So you know that these functions don't come, when you see them in the concept of logistic regression and all these things, don't come from nowhere. They basically there's some mathematical reasoning with why they are the way they are. So this is the softmax function, and it's called softmax, and actually we will see this in plots as we go along. It looks like a soft version of the maximum function. So in any event, we can fit the distribution exactly to our exponential family distributions, okay? And this alpha is not anymore 0, but is log of the summation of these exponentials. And later on, we will see that, imagine here you have a log of the summation of the exponentials, okay? And this will give us headaches later on numerically, because this is not an easy term to compute, all right? But these functions are never easy to compute, okay? Because even in a physical context, in the physical world, have significance that is very complicated. But here we have a log of the summation of the exponentials, okay? So we need to deal with these things one way or another. Okay. I think I may need this if I have time for my example. For the bigger distribution, you can also write it as an exponential family distribution. So the natural parameters, you may want to remember, because I may use this on the fly, that there are A minus 1 and B minus 1. So A and B come in the moment parametrization. Eta comes to be, there's no algebra really, it's just looking at it. And then this function alpha comes to be the log of the gamma function A gamma of B divided by gamma A plus B. Okay. You may ask, who is Gaussian? Come on, Gaussian, of course, exponential family, right? Come on. There is really nothing to fancy about the Gaussian. We already have done it because we discussed about the canonical form of the Gaussian. Let me prove another item from your homework. All right? Has anybody shown this already? Have you looked at this, or you were waiting for your TA to come? Because he told me after I discussed this in lecture, he's not going to do this. Okay? So, how about this amazing result? And you tell me if you like it. If you want to calculate the expectation of the sufficient statistic, it comes to be equal to the gradient of the function A with respect to eta. This is not an approximation, this is an exact answer, an exact result. The expectation of U of the sufficient statistics, it comes out to be the gradient of A with respect to eta. Anybody who already proved it? All right. Our TA, he proved this when he was flying back. He said, to keep my brain alert, I'm going to do this calculation. Okay? While at the same time drinking the last beer coming from Ireland, I suppose. Okay. So here's the calculation, and see how simple it is, right? This is our distribution in the general form. So what I'm going to do is, I am going to take, if I normalize this, if I integrate in x, I get equal to 1, because this is a normalized distribution. So consider an integral of this equation, the second equation, integrate it in x, equal to 1, and take derivatives with respect to eta. Take derivatives with respect to eta. So there is an eta there, so gradient of g times the integral of the rest, and then there is g of eta, all right? And then you're going to have the derivative of this with respect to eta. You're going to get a u outside the exponential. We agree? All right. So do the following. Multiply here by g and divide by g. What is g times this integral? What is g times this integral? This integral times g, how much is that? 1. So if you put this term on the other hand side, on the right hand side, you're going to get minus gradient of g over g equal g of theta times and this term. And what is that? What is g of theta times a times that? That's our distribution. And then I have the integral with this distribution of u. What is that? By definition, is the expectation of u. So it comes out that the expectation of u is exactly the gradient of A with respect to eta. Now, I mean, it's a coincidence. You will say, well, you know what? This includes many, many, many distributions. So basically, it's extremely desirable result, okay? And can you push this further? Yeah. You know what? If you take the second derivative of A with respect to eta, it comes to be the covariance of u of x of the sufficient statistics. And if you want to go to higher order models, you can keep going. But there is an important result here, okay? Do you agree that the covariance of u is, positive, non-negative, yes, positive, semi-definite, basically, all right? So what does it imply for the function A of theta? What type of function then A of theta comes to be? It comes to be convex. And if the function is convex, you know what that means? Look at this equation. You don't have to read everything. We just proved basically the function is convex, okay? And effectively that means if you look at this equation, right, the moment equal to the expectation of u is equal to the gradient of A. Because A is convex, means this equation of mu equal to gradient of A, it's invertible. So for all of these distributions, you can write uniquely eta in terms of mu, the same way you can write mu in terms of eta. So there is no ambiguity, there is no like multiple solutions or anything like that. You can go from the moment parametrization to this natural coordinate theta in a unique fashion, and we will actually take advantage of this in the context of some regression problems we're going to look, maybe not today, but certainly on as a starting point on the lecture on Wednesday. So this equation and the convexity of A implies, again, that mu uniquely defines theta and eta uniquely defines mu. And in the examples in the homework we are going to submit, you will actually show this for the different distributions. Do I really need to prove to you that u of x is the sufficient statistic? All right? You guys read, okay? It is exactly the same thing as discussed before. U of x is the sufficient statistic of that distribution. Here I have the same picture I had before, so you can look at it, okay, study it, and convince yourselves that the only thing you need to know for estimating the parameter theta is the sufficient statistics u of x. All right. And actually this is what is called, that factorization that I already talked earlier today in the lecture is what's called the Neymann factorization theorem, that basically it's equivalent to the decomposition that you see here. You remember before we had a function of theta multiplying the sufficient statistics, there it is. Then we had a function of x, all right? So this fits exactly in the same setting that we had before. Okay, you know what? If we are lucky, I have 4 minutes, and I'm going to show you another amazing result. So let's do MLE estimate for the exponential family, okay? So you collect data from any exponential family distribution, x1 to xn, okay? Then immediately I claim that the sufficient statistic, after I collected this, is basically the sum of the sufficient statistics of u of xn. Can you see that? Right? If I multiply all of these exponential families, what do I get? I get the product of these h's, okay? Then times g of theta to the power n, and then in the exponential I'm going to get summation of the u of xn. Now, what is important, right, and this is not a trivial thing, is that it doesn't matter if you have a billion data set, the statistics that you get, the sufficient statistics to describe this distribution, is of finite size. And in this particular case, the sufficient statistics is a vector of dimensionality the same as eta. It doesn't grow with data. Other distributions don't satisfy that. Okay, in the exponential family, the size of the sufficient statistics is always finite and is defined by the underlying distribution, the size of eta, basically. Okay? So let's do a maximum likelihood estimation, right? Not that we're interested on MLE, but to see other good things that come out from the exponential family. So how do we do maximum likelihood? You take the log on the second equation that you see. This doesn't depend on the parameter theta. From here you get n times the derivative of A. And what's the derivative of A? We prove it exactly. It is the expectation of the sufficient statistics, okay? All right. And this time what derivative will give you the summation of the u of xn, all right? So if I put all of this together, put the n on the other side, you get the following amazing result. That the gradient of A calculated at the maximum likelihood estimation for the parameter theta is the sample mean of u. Okay, the sample mean of u. But it comes out, right, you already know that this gradient is exactly the expectation of u of x. So here's the amazing result. The this equation that you see here, to compute the expectation of u, all right, you don't really need to go and calculate the parameters eta at the maximum likelihood estimator. The only thing you need to do is take the sample mean of u, immediately that will give you the expectation of u of x. So actually, the calculations that you will do there in reverse order, you will do this, and then from there you will go and calculate what the eta is that leads to this result. And I believe, I don't know if it's on the next slide or not. I have 1 minute, so this is a demonstration of this for the binomial, the Bernoulli distribution. So in the Bernoulli distribution, right, so if you want to calculate the expectation of x, okay, so the MLE estimate is the same as the sample mean of this indicator functions, right? Why this indicator functions? Because u of x equal to x, right? And x can take value 1 or 0. So here is the estimate of mu at the MLE, and then how do you calculate eta? You go to this formula that uniquely relates eta and mu, and you say eta at the MLE is log of mu bar divided by 1 minus mu bar, okay? So what we will do on Wednesday is the following. I'm going to define a prior distribution that is conjugate to exponential family likelihoods. I'm going to define one posterior distribution that's applicable for every problem. I'm going to define a predictive distribution that's applicable for any problem in the exponential family, and then I will convince you that effectively you can cut and paste and adjust the results for different problems by simply looking at these general formulas. Okay? So I'm going to try to post the lecture early on because the lecture on Wednesday may be a little bit heavy in equations, right? But apart from that, should not be anything major. All right, see you next Wednesday.